let's begin by recalling the definition of natural transformation, as the diagrams already indicate. So remember that we're going to consider the family of functors between two given categories. So this is symbolically a set of functors between our two categories. And if you remember, to recall some definitions from previous lectures, we saw that the category of categories is itself a category. Right? So I failed to give it a name because I left it as an exercise, but let me just recall that what I mean by this is if we define cat as the category of cats, not the category of the animals, but the category of categories, as the family of all categories with functors as morphisms between them, and with functors as arrows, then what I mean by this notation is simply this notation. So this cat is the category in which the objects are categories themselves, and arrows are the functors that we defined in the second lecture. Okay? So what we're doing by looking at the possible functors between two given categories is, remember, in the categorical picture of a category and its objects, what we're looking at is at the collection of all arrows connecting two given objects. It's just that now we're in a somehow a higher step of abstraction, and we're taking two categories and all the possible natural arrows between them, which are the functors. So these things are the same. I mean, it's the same notation and just somehow tidying up the notation that I introduced for the sake of consistency with the previous material. Okay. So, okay, let's introduce again natural transformation just briefly. So remember that the notion of natural transformation appears when we look at this family of functors. Remember, this is a family of all the possible functors between the categories. And we, again, this sort of degenerate way of thinking of even more abstraction, we take these arrows now as our objects, and we're going to try and think of arrows between these arrows. And remember that those are the arrows between the arrows of the categories. So we are doing the arrows of the arrows of the arrows, which is fine. Everything is fine. So the notion, I mean, okay, let's reflect that we're doing the arrows of the arrows of the arrows by writing double arrows. So yes, we do something a little bit special, but not too much. So remember that the idea of a natural transformation was to think of our functors between two fixed categories as objects in some hypothetical category, and the natural transformation will be the arrow of that, the notion of morphism in that category. So taking the space of arrows of this category of categories, and then taking those things as objects, and then define a categorical structure. Okay? I'm just saying the same thing over and over just for you to see that this is a bit of gymnastics, but we're not doing anything too complicated. It's just sort of employing the basic definitions over and over again. Okay, so let's just diagrammatically depict how these things work. What happens when I have a functor? So what happens is that objects get sensible. Okay, so let's introduce the color code. I think it's going to be useful. So let's denote this thing with an F. So what happens is that objects get sent to objects. So this is the image under F of B. This is the image under F A. And of course, we also have the arrows themselves being mapped with the function. This is, let me write it here. This is the image of the arrow F under the functor F. So similarly, because I'm considering two functors of between two fixed categories, I'll have the similar story for these guys. This is G, and G, of course, maps the same way. Maps the objects to the objects, and the arrows to the arrows. Okay. So what we want is to give the notion of an arrow from F to G. So this diagram here gives us, or somehow suggests, a possibility for an arrow between functors, simply as, okay, these pairs of objects will in general be different if these two functors are different. So the only way that we have to connect objects in a category is via the arrows of that category. So having a natural transformation between F and G will correspond to being able to relate these two objects in this particular direction, because we want arrows to be directed. It's no problem. Then we want to define the equivalent thing from G to F. But for now, we want the direction. And remember from our third lecture that there's a natural property to ask from this kind of diagram, and that is that the two possible arrows that could be composed here, going through this upper path, where we go from FA to FB and then to GB, so composing this arrow to this one, will be a different arrow in principle from going from this bottom path, where I go from FA to GA and then to GB. So demanding that this diagram commutes means that these two arrows are the same, and that I have a commutative diagram. So only the arrows that are displayed on the diagram are the arrows that are different in the category. Okay? So the way we're going to formalize this notion is by giving the definition of, I think I'm done with colors. It's going to be by definition of natural transformation. So an alpha is going to be actually a collection of morphisms from the pairs of objects mapped with the two different morphisms that we're trying to relate. And this is going to be for every object in my category. Right? So this is the basic information. This is basically the bag of all the yellow arrows here that will allow me to close the diagram. And the condition that all these diagrams are commutative is written more explicitly here as, well, actually, you can see it very explicitly here. So in here I have the alpha for the object A, and in here I have the alpha for the object B. So it's in this diagram that I can impose the condition that the natural transformation family of maps commutes, or makes the diagram smooth. Very well. Okay, so this is a reminder of the notion of natural transformation. Any questions about the notation or the basic definition? Okay. So the one thing I wanted to talk about that I didn't have the time to cover yesterday in a little bit more detail, and somehow commenting a bit more about the subtleties in the interpretation, is the notion of isomorphism and why it's not reasonable to think of equality in a category as your notion of equivalence somehow. So remember that when we introduced categories on our first lecture, we said these are collections of objects, that we call them objects to refer to the abstract nature of these things, that can be anything, and the only thing that matters is that we have this arrow structure that allows us to interpret diagrams and sort of walking from one to the other and composing paths and so on. And we said, well, equality in this context is going to be a very philosophically unstable notion, because for the exposition, equality meant that the two symbols had the same, sorry, the two objects had the same symbol denoting them. So obviously that's a very unsatisfying notion of equality. You want equality to be characterized in a more formal way. And so throughout today's lecture, which is the final basic lecture on basic category theory I'm going to give to you in the summer school, I want to emphasize this notion of the structural relatedness of categories. So categories emphasize the relations between objects, so the connectivity and the directionality of relations between objects. And it's that what gives the characteristics of a category. Is that what essentially gives you the information of the structure of a category? Not so much how objects are distributed or how they operate in more algebraic ways. It's more about how they relate to each other. So in the second half of the lecture, we will introduce a first example of what's called a universal property. So if any of you are familiar with any form of abstract algebra, maybe you've heard of the term universal property. Many times it's referred to when a tensor product is introduced, and if a lecturer has the decency to refer to what is the definition of tensor product, they will say, well, this is defined with a universal property, and they will basically leave it at that. So the universal property of the tensor product is quite subtle for an introductory course. So what I'm going to do today is give you the universal property of a categorical product, which is a categorical generalization of the Cartesian product of sets. And there you will see this idea that we give a definition of a categorical notion, so some structure, some object, or perhaps not object, but some construction within a category, by essentially saying, if I have arrows to this object, I want to characterize what happens when I have arrows from that object to every other object, or from every other object to that object. Okay? So our emphasis is on how those objects relate to all the other objects. If we want to identify special objects in a category, we need to say how all the possible arrows going from them or to them are going to be found in the category. Okay, so that said, let's think of one particular example of category to exemplify this instability of equality versus isomorphism. I'm going to throw a question, and feel free to answer in Spanish if you want. But I think all of you will have an answer. It doesn't have a correct or incorrect answer, and I want you to give me some answers. I want you to tell me what a sphere is, in particular a two-sphere. Someone give me the most mathematically precise definition you can think of a sphere. It doesn't need to be, completely formal. Definiciones de la esfera, de las dos esferas. ¿Cómo definís las dos esferas?
Las dos esferas. Mucha diferencia.
No.
¿En dimensión 2 has dicho?
Sí, dos esferas, en tres dimensiones. La cáscara de una bola.
Ah, pues el conjunto de puntos que están a la misma distancia.
Ok. ¿En qué espacio?
En R3.
En R3. R3, vale. R lo identificamos con un espacio que conocemos bien. R3 tenemos una distancia, ¿no? ¿Alguna definición más?
Si no tengo una distancia no puedes hacer eso, o sea, también lo puedes definir como topológicamente, ¿no? Supongo. En plan, superficie compacta de género 0 o algo así.
Muy bien. So yeah, that's the direction I was aiming for. So there's what is the two sphere? Is it in a fixed space with a fixed metric? Is it radius 1, radius 2? What is the radius of the sphere? Is it, if I deform the sphere a little bit, is it still topologically a sphere? So if I'm talking about topology, can you distinguish between a sphere and a complicated shape that is still the same topological genus? You can't. So the idea that we mathematicians and physicists and scientists give names to things and give one single symbol to a notion, it's somehow kind of misleading because we're very quick to say, oh, we have this symbol, that's it. It's very simple, everyone understands the same. But if I write the symbol for a sphere, the conventional symbol for a sphere, S2, on the blackboard, depending what kind of mathematician or scientist is looking at this, they will understand completely different things. And they will all be correct in their own sense. It's not that they are worse or better in understanding spheres. They will just have completely different notions of mathematically rigorous definitions of sphere. And the topology case is, I think, the most illustrative, that we have all these different definitions of what sphere is. So for example, sphere is the one-point compactification of any Euclidean space, or in this case, a three-dimensional Euclidean space, or in fact, any space homeomorphic to an Euclidean space. It's also the locus of any monotonically increasing function in some metric space, like the radius and these kind of things. So there's all these different ways to define a sphere, and it really depends on what you mean, but how things are similar in that category, hence the name category theory, that gives the notion of sphere as something precise, as something rooted. So it is in the sense that, for example, if you're doing differential geometry and you're particularly thinking of metrics and Riemannian metrics on spheres, then you definitely don't have one single canonical definition of sphere. Because how do you choose what is your model sphere unless you artificially say, this is my model sphere, and you point to it? There's no notion of what is the one natural S2 sphere. You would say, well, I have a class of manifolds that are diffeomorphic, or have topological continuous maps between them, and they have different metrics. They have, as Riemannian manifolds, they are different. If you want to walk on them, the experience will be different. But in a topological sense, or not, differentiable topological sense, they will be the same space because they will all be diffeomorphic. So they will be isomorphic within the category of topological spaces, that they will be not isomorphic in the category of Riemannian manifolds, for example. Right? And so it's this idea that you really need to make precise what you mean by morphism in a certain context for you to speak of the objects in the first place with some precision. So when I write S2 on the blackboard, or A in a category, now we're going back to categories, enough geometry. So when I write down a symbol for a particular mathematical notion, it's not entirely clear what I mean just by that symbol, and by that symbol, unless I give you some structure of how to think of when things are similar enough that you can say, okay, they are interchangeable for this particular notion of relatedness or sameness, right? So, or similarity somehow. So this is the notion of isomorphism, and we already covered isomorphisms at a more formal level, just formal definition as the existence of a pair of arrows in the category, such that, because in a category we always have the identities, remember, we never write them because they're always there. This direction F, G. So demanding that these two maps compose the arrow from A to A and B to be precisely like the identities is what we define as an isomorphism. And I will use a symbol that you're probably very familiar with. We say that they are isomorphic objects within this category. And I want to be pedantic and say these objects are isomorphic in the category A. And it's crucial to say, and I hope that my previous rant about spheres gave you a sense why it's important to say in which category things are isomorphic. Because obviously, if you're walking on Venus or on Earth or on Jupiter, your experience is going to be very different if you want to reach from one pole to the other. And they are all topological spheres. So if you're just a topologist and you want to do some astrophysical studies, you're going to have a very bad time. If you think that Jupiter and Mars are essentially the same. So it's very important to specify that. But in any case, we do have this notion in a category. So this is, in our convention, we said that equality in a category is very strict. It's as strict as basically saying this object is the only thing that we can distinguish from anything similar to it. But then we have this more flexible and more natural, and the key word here is natural, notion of isomorphism, where we can see objects in a category that are naturally similar for the specific characteristic that we are interested in. So that's, and I hope that this is helping you realize what categories are. Categories are a symbolic game of arrows and points, yes. They can be seen as just games, but this is more conceptually what categories are. Categories are a choice of what are the relevant aspects of certain mathematical constructions that allow you to identify what sameness means or similarity means between different elements or different kinds of those mathematical constructions. So when I ask you for examples, most of the hard work required to come up with good examples of categories is to think of probably familiar stuff that you've already considered in your life before, but you have to look at them in a particular, from a particular angle and think, okay, we're going to look at this particular property of these particular objects. And then the notion of morphism is usually very natural from that point. Okay, so enough with this more sort of philosophical discussion. And everything to say that whenever we have a category, we have a notion of isomorphism within that category. Okay, and it is that notion that of what the similarity of objects is really about in the context of category theory. Okay, so back to our discussion about natural transformations and functors. So we have defined the category of all categories, whose arrows are just the functors. And now we have identified that if we fix two categories, we have the notion of a natural transformation. So this notation here, perhaps I can refine a little bit my comments by saying that it is the objects of this, which is the category of all the functors between two given categories. The objects are all the functors between the two fixed objects, hence the notation reflecting explicitly the two fixed categories. And then the arrows of this, so if I want to say two objects in here will be a functor from A to B and a functor from A to B, right? So this is, these are two objects. Remember this notation. Remember, where do I have that notation? Here. Have the name of a category and then brackets the two objects, and that means all the arrows between the objects in that category. So now I'm taking two objects of this category, which are functors between the two fixed categories, and I'm saying I'm going to write the name symbol for that category in front. So what this means is this is the set of all the arrows in this category. So what is this? Well, this is precisely all the possible natural transformations between F and G. It is set, natural transformation that we just defined. So how do we write this? So fixed A, B, and fixed F and G, two functors. So this set, this collection here, is all the possible natural transformations. Okay. So alpha, beta, all those kind of things. Okay. Of course, by the way, but just bear in mind that I can change these two functors. So I could write G here and F here, and in this larger category of bracket AB, I have natural transformations from G to F, but also from any two other pairs of functors between the two fixed categories. Okay. So I want you to bear with me and realize that, okay, so we have a notion of isomorphism of category, right? So we have a notion of sameness of two categories already because we identified the category of all categories. And therefore, well, there is a notion of an isomorphism in any category, in particular in the category of all categories. And so let me be tidy with the notation here. Just right here. A and B are isomorphic if we write isomorphic as categories when, and of course, I'm just going to rewrite what I just erased, which is the definition of isomorphism, F and F dash, between A and B, with the property of isomorphism, which means that F dash goes with F, is to compose to the identity in the category A. So this is the identity functor. And this is the identity functor. And at the okay. So this is the notion of isomorphism of categories, but remember that what are these objects? So again, just to review, this is the notion of isomorphism in the category of categories. Therefore, that's why I call these two categories isomorphic. They are isomorphic within the category of categories. But if you take to heart this definition, the fact that there is a natural notion of arrow between morphisms, and that's where the name natural transformation comes from. This is a natural notion of arrow with a direction between two functors. And we have identified this bracket AB as a category of all the functors between two fixed categories, with the arrows being the natural transformations. Then you realize that if I'm in this kind of situation, I'm not yet assuming that this is an isomorphism in the sense of categorize. I'm just assuming that I found two functors in this direction. I realize that I can compose them. So F composed with F, so F dash composed with F in this way. I can, so this as a functor belongs, according to that notation, to this, right? It's a functor from A to A. I'm just going from A to B, then back to A as a category. And similarly with the other composition. Right? So this, yeah. So now we have, of course, in these categories, we have the identity, the natural transformation. This kind of transformation you would have found in the exercise when you proved that these arrows are between functors are indeed arrows of some category. We also have the identity functors in here. These are functors that, yes, the identity functors, the functors that basically do nothing. So now we are in the position to say, okay, so we have two elements, two different elements. Let's focus on A at first. We have two different elements of a given category, which is the categories of all the functors, all the autofunctors, this is the usual name, of all the functors of A onto itself. So the natural thing to impose is not that they are equal, because remember we were justifying why equality is unreasonably strict for this notion. So what is the natural condition to impose here? That these two functors that belong to this category of all the functors from the category to itself are isomorphic within that category, not necessarily equal, right? And so we want to impose. Let me keeping the diagram all the time, but I hope everyone sees. Right here. Let's say A and B are equivalent. This is the other notion that I was referring to yesterday. I didn't have time to elaborate. If I'm basically going to copy the same thing, I'm going to use a different symbol, has one less little dash for the equal sign. And, well, I'm essentially copying what's over there. But now what I impose is that F dash is isomorphic in this category to the identity functor. And F dash F, I'm copying again. Oh, what's that? Is isomorphic in this category to the identity functor. Did everyone follow my definition of equivalence of categories? Because I think this is what exemplifies the philosophy of the categorical way of thinking, at least at the level of the functors. make sure I'm not running too much over time. Okay, we're on. So that's it. We have two notions of similarity between categories. But because category theory, as I was trying to convince you, is concerned with how arrows behave, and not so much objects, and demanding equality of objects is unreasonably strict, precisely because I have all this freedom, right? In topology, what is a sphere? Well, it's an equivalence class of isomorphic, in some sense, spaces, as are all topological spaces. So it's always the philosophy is always to use the natural notion of isomorphism in whatever category you're in to signify equality, to signify sameness to the best of your knowledge, so to speak. And then if you follow that philosophy, as a recap, we have categories as arrows between objects, then we have functors as the natural notion of arrows between categories themselves, and that itself forms the category cat that I erased. And then when we fixed two elements of cat, all the possible functors between those two fixed categories are linked by natural transformations, which we can then prove that form a category themselves. And then we're essentially done with the sort of levels of abstraction, and we realize that if we are comparing functors, because that's what we're doing when we're comparing two categories, we have functors that go back and forth and somehow relate them mutually, both A and B. The natural category that we are in is the category of all functors from A to A, and therefore it's natural to demand that they are isomorphic within that category, not necessarily equal. So when they are equal, we call the categories isomorphic, and when they are and when the sort of inverse functors are only isomorphic as functors, we call them equivalent. Okay? All right, so this is it for all this business of natural transformations, arrows. And we're moving to products. So the notion of a product, as the name suggests, or the notion of a categorical product, as the name suggests, is essentially putting some extra structure on your category so that you can operate your elements, your stuff in the category. And so remember, what is your stuff in a category? It's both objects and arrows. So the only somehow subtlety of our definition of an operation within a category is that we will have to account for objects operating in pairs or in triples or in n-tuples, and also morphisms operating among themselves. So for that, we'll just briefly introduce the notion of, first, I'll define categorical product, binary categorical product in general, and then we'll see how the usual Cartesian product of sets, the direct product of taking pairs that you're all familiar with, is an example of this. And you'll probably see that it's directly inspired. The definition of categorical product is directly inspired by the Cartesian product of sets. Okay, so let's see. So let's define a categorical product. I'm going to use a symbol that is already telling you that this is inspired by the Cartesian product. So what is this? So I have two objects in a category. So this is a categorical product. Product. It's a pair of a category and an operation that I'm going to describe in a couple of steps. So first of all is an assignment of pairs of objects in the category to a single other object in the category. Okay, so far so good. But also, this object will carry projections which are two arrows in the category that take me back to each of the two factors, so to speak. So there's a pi1 that goes to the first factor, and there's a pi2 that goes to the second factor. Again, this is probably already suggesting the Cartesian product, but for now I'm just giving you a categorical definition. I'm just saying you take two objects, associate the third one, and that third one needs to carry two arrows to the two previous objects. That's what I'm saying. I'm just using the categorical structure.
The category is the objects or all the category? Es decir, que cuando dices A, B pertenecientes a la categórica, ¿es la categoría o la familia de objetos?
La familia de objetos.
A ver, lo suponía, pero tenía que preguntártelo, ¿no?
Yes. As usual, we are doing the convention that the name of the category we use as the name of the objects. But yes, you're absolutely correct. This is the objects of in here, just for consistency. Here, just to be completely precise. Yes, it's the objects of the category. But we've been using that convention throughout this course. Okay, so we have those two maps, and then for these to be a categorical product, what we are going to impose is what's called the universal property. And this will be, unfortunately, the only example I have time to give you of a universal property construction in a category. But I think it's a good one. It's an illustrative one, and it's very simple. So, the universal property. As the name suggests, universal property, it's saying something that our product needs to satisfy with respect to everything else in the category. It needs to be universal with respect to everything else in the category. So what that means is, I have a third object here, have A and B, and I take their categorical product. So I have 4 objects in total. According to this first element of our construction, we have an assignment of objects for any pair of objects in the category. So we have these 3 objects. And now let's consider a third unrelated object in our category. This could be any other object in the category. So of course, from the second line of our definition, we know that we have the projections, right? And then what we say is, okay, for all arrows, okay, if there are no arrows, let's be a bit more intuitive. If there are no arrows between C and A, which is possible, because we are not in a category, then there's nothing else to say. There's no possibility to demand anything. There's no interaction between C and A and B. They don't talk to each other at all. But if there are arrows, and so for all the arrows that may exist between C and A, if one third object is related to both A and B, I'm not assuming anything about these arrows. I mean, there's nothing to assume. I have no structure. This is just a category. It's like bare bones of formal structure. There's nothing else to demand. So if I have 2 arrows between an arbitrary third object that are connecting C to A and C to B, then it's natural to demand that, okay, there should be an arrow from C to this construction. So I want that there should be an arrow from the third object to the product, because somehow if the categorical information of the 2 objects gave me the product, and the categorical information told me that C is connected to A by a little a, and C is connected to B by a little b, I want to demand that my definition of categorical product is such that information is enough to say that C is in fact related or connected to the construction by a map. Okay? And can anybody guess what I'm going to demand for this? So what I'm demanding, first of all, is that there exists a unique C mapping, let me say, C mapping C to A to B. There exists only one, but that's very oblivious of. I mean, okay, this is somehow motivated by this fact, but I also have these 2 arrows. So can anybody guess what I'm going to demand here for this C? That must be unique.
Que la composición de pi1 con C será igual a.
Efectivamente. That means that this is commutative. This diagram is commutative. That going from C to B via little b is the same as going from C to B through A times B. And similarly for this other half of the diagram. And I could have defined a product of n different objects just by giving n different projections. So we demand that this exists and it's unique, and this diagram commutes. Remember, we use this symbol hashtag thing here. So this commutes. Okay, so that's the definition of categorical product. Quite easy. So this could be left as an exercise, but I'm going to do it here, essentially. And the exercise is to show that when the category is set, so what is set? Set is the family of all sets, and the arrows are just the maps between the sets, or also the mappings for pointless elements. Okay? So your exercise is to show that set with X Cartesian product is a categorical product. So that's the exercise. I think basically that needs to go. So that's the exercise, and that's the end of my category theory course. Let me just give you a sketch of why this works. I mean, what I wrote here is essentially the definition of the Cartesian product in some sense. The only thing that is not explicit is how C is determined by A and B. In a general category, what I had to use, because I didn't have, actually let me use this last 5 minutes to do this a bit more complete. So imagine that now that diagram, everything else is the same, and in sets, I take two sets, I create a new one with a product, and then two maps that way. So what are the maps? Remember that A times B for sets is just the set of all the pairs. This is that. X and Y. Is the set of all the pairs such that X is in A and Y is in B. Right? So I have a natural projection, hence the names, to each of the factors, because I can project to the first factor from here A, simply because if you give me a pair of numbers, I can give you, I know how to count, so I know what's the first and I know what's the second. Right? So I can, because I know the structure, how these things are defined with elements of sets, I know that I can project them down. Right? So in this case, the projections are simply, they simply reflect how I constructed the Cartesian product in the first place. Okay. And actually, everyone's familiar with this, but perhaps what people might be less familiar with is the universal property of the Cartesian product. Because nobody, I mean, except here, very few people care about the universal property of the Cartesian product, which is usually not that interesting to think about. But it's there, it's definitely there. So what does the universal property say? It says that when I have this diagram, set phi, set C into, so there's a map A into set C, there is a map B into set B. I take the Cartesian product, these two sets, which carry the canonical projections. What is the universal property? So the universal property says that there should exist a unique map from C to the Cartesian product such that those diagrams commute. So one way to show that this is the case is to construct the map explicitly. I have explicitly means as a map of sets. I have explicit expressions for or explicit constructions for the projections. So why not give explicit construction for this map C? Does anyone know how to, and as you've seen this before, otherwise refrain yourself from answering. Does anyone know, has an idea how to define C? Any ideas? It's a puzzle. You have some ingredients, you want something to happen, you can combine them in very limited ways. So there's not many possibilities to make mistakes.
¿Podrías hacer la composición de la inversa de la proyección?
Las proyecciones no tienen inversa. Son sobreyectivas, sean privadas. O sea, que no podemos, a priori, esto no existe en general. Notice that the information you must use is A and B.
El producto cartesiano de A sobre un elemento de C por B sobre un elemento de C.
Efectivamente. So that's what's usually called the Cartesian product of maps. So C is what in the literature is written as this, and what it means is C acting on an arbitrary element is given by the pair A on that element, B on that element. It's a very silly definition. I did nothing, essentially. But it is a map, it's a well-defined map, and what's most important is that if I take the first component, which means projecting, I get the image under A, which is this triangle commuting. If I take the second component, the second one, which is this other triangle commuting. Okay, so that's the hidden universal property in the Cartesian product that gives the motivation for this more general. But here the punchline is that in a category, because we don't have access to this level of somehow granularity, we don't have access to projections telling us how elements behave, and so how the sort of fine structure of our objects behaves. We need to resort to this other philosophy. We need to resort to the level of how does the object as a whole relate to other objects in my category, and when that information is known, I need to impose that information is enough to determine the relation between that new object that I define to any other potential object that might be related to the other two that are constructing the object. Okay, that is what every year I try to tell you, but obviously in 2 hours in course this year I managed to put a universal property in the black course, so I'm happy. So that's the end of my course. Thank you.